Our next speaker is Michael Koets from SWRI.
Hi there, I'm Mike Koets from Southwest Research Institute. I'm going to be talking today about some work we've been doing over the last couple of years developing a domain-specific programming language that we call RITES. This is a domain-specific language. It's really focused on describing how software and firmware execute with respect to time. So the language itself is agnostic to if it's software or firmware. What we're focusing on is addressing reasoning about and representing time. So we're going to spend a couple of slides talking about why we pursued this, why we looked at this problem. One of the key things is that scheduling and timing are very important to a lot of space, software, and firmware systems, and embedded systems in general. Here are some examples of things where you would need to be able to reason about time, would need your software or firmware to execute in a particular time frame with very precise timing. So we're talking about things like interfaces and protocols for communicating between devices. These may be serial communications flows. These may be command sequences and handshaking processes. Any sort of time division multiple access protocol, of course, heavily depends upon fairly precise timing. That may be wireless, or it may be over some sort of wired serial channel. Often, if you're doing very fine-grained scheduling of computation or any sort of pipelining, you may need to very precisely sequence and time operands and operations going into your software. In the case of firmware, you may have very precise coordination requirements on the firmware modules. Cases of hardware control, things like powering up radio amplifiers, control of actuators, control loops, all of these things depend on very precise timing. Similarly, periodic or scheduled sensor collection, and also test scripting. As we saw yesterday afternoon, there's lots of cases where you would like to very precisely time test inputs to systems you're trying to test. So there are lots of applications, very realistic, where we need to find some way to make our software and firmware behave in very precise times. And not just meet deadlines, but actually have events happen exactly when you want them to with perfect reproducibility, perfect predictability. Unfortunately, the languages we use to develop these systems really have no built-in semantic concept of time. On the software side, we're often using languages like C or C++, which is focused on organizing data, doing computation, really has very little concept of time. Often, C programs do not execute deterministically, particularly if there's a cache involved or any sort of sophisticated processor that may be reordering operations. You may fall back on a real-time operating system to provide some sense of time and scheduling, but again, it's going to be at a coarser level and primarily about meeting deadlines more than precisely scheduling. So you're probably going to have to fall back on using hardware components, timers, interrupts, that kind of thing, to get any sort of precise timing. Verilog is a little better. Verilog is, of course, the language you would use to develop a lot of, an example of a language you would use to develop firmware for like an FPGA. But Verilog is focused on register transfer, again, computation, updating registers. You do have more deterministic execution, but the timing granularity that is very, very tight, maybe nanosecond timing, and any sort of higher level timing concept is just absent from the language. So what do? We need to deal with time. Our languages don't support that. How do we deal with that? Well, we hand code a very complex timing infrastructure over and over again. We create the data structures, execution paths to realize some sort of timing behavior. We'll try and interface to timing services that are available in the hardware, like timers or periodic interrupts. We're often writing a lot of loops, a lot of counters. And when we do this, we tend to do it over and over again from scratch each time for each new project. This is not the kind of thing that gets reused a lot. There's some problems with this approach. You have to write a lot of code. All of this timing infrastructure, you tend to rewrite over and over again. And of course, that's a lot of code to debug as well. Can be difficult to extend and to modify. This morning already we heard a couple of talks addressing the importance of being able to extend and modify our solutions. When you hand code these sort of timing infrastructure, it can often be very dependent on the specifics of what you're trying to implement. And if requirements change, maybe you didn't understand something, maybe the scope of the project changes, it can be very difficult and a lot of work and error prone to go in and modify that infrastructure you've created to meet the new timing requirements. Also, this can just be challenging in general. It's very easy to get wrong. So we looked at all these problems, and we realized that we were seeing these kind of problems over and over again, and thought it would be nice for people to reason about time directly. We'd like to have some way that we can express timing in a more formal, direct way, making it easier to connect things like specifications and implementation. So when we have requirements on what the software and firmware must do, they can often be represented in terms of timing diagrams or requirements text that addresses timing issues. We'd like to be able to take those kind of requirements and more directly map them to the artifacts we're building as we implement the software and firmware. And maybe even more importantly, we'd like to have a better mechanism to very rapidly and robustly respond to these kind of changes. Maybe there's changes in the component timing characteristics. Maybe we need to change the FPGA clock frequency because we need to lower the clock rate to reduce power consumption. Or our design has become so complex we can no longer close timing on, at the rate we'd hope to. Or environmental considerations require us to lower the clock rate. We'd also like to be able to just extend the capabilities, add additional features, or take on the software and or take on additional responsibilities into the software or firmware because of some unknown characteristic of the hardware that's discovered late in development. So the way we address that, the technique we developed to address being able to directly reason about time is to develop a domain-specific language. We call it RITES. It's a very compact and precise description of when things happen. So it's a domain-specific language. It is not meant to be a general-purpose programming language. It is not meant to solve every problem we're going to confront in a design. But it does give us an ability to create parts of the design that deal with precise timing in a very succinct, very clear, very easily modified sort of way. So this language has a syntax and semantics that deal directly with time, concepts like delay, like detecting changes. We support transient actions where we're doing something briefly and then doing something else. But like I said, it's not a general purpose language. It's focused on coordination and not computation. It has very limited computation capability. It's not a universal language. But what it's meant to do is develop modules that will let you coordinate when things happen, coordinate other pieces of software or firmware that are doing the computation, that are doing the actuation, and it's just handling the very coarse level scheduling of that. And I'll go through some examples to try and clarify that a little bit. So we have a language that talks about time, that lets us reason about time and express concepts of time. But we also have code generators that take those programs written in this RITES language, and create executable forms of them that we can actually put on a design and actually make run and do something. We have code generators that produce ANSI-C for running on a microprocessor, Verilog, which is an HDL, which allows us to implement these programs in an FPGA. Important for space applications, we also have code generators that produce Verilog with built-in triple modular redundancy. I'll talk a little bit more about that, but basically those are features to let the HDL work on non-radiation hardened devices in radiation environments where you might have transient errors. This helps protects the function against those kind of things. In addition, we have a few other code generators for a deterministic subset of the language. This is part of the language that just executes a sequence directly and then finishes. We can generate static artifacts like lookup tables or even mechanical cams that will implement that kind of timing characteristic in some other forms other than Verilog or C. So to put this in a little bit more context of what we've heard about today, this is a way that we have chosen to try and do software reuse that kind of lands between just reusing functions or modules that have been written, just taking that code as is and trying to move it from project to project. So working a little bit higher level than that, but at a lower level than patterns. This gives you a capability to reuse everything we've learned about how to implement precise timing without being quite as abstract as a design pattern. So this is a domain-specific language that captures what we've learned about how to implement timing and rolls it into the language itself and lets you focus on the project-to-project variations and what kind of timing behavior you want. And everything we've learned about how to implement that timing, it's built into the language. So it's kind of a middle road of reuse that we hope will be effective. So here's the design flow for the RITES language. On top left, you see the timing language program. So this is a program you write in this new domain-specific language. We have several compilers that are basically code generators that produce either C code or Verilog code or some of these statically generated artifacts. But you always take that generated code and you incorporate it with other code that's developed by other means. Code to do the actual computation, the code from some of the frameworks we've seen today, those kinds of things. It's just a module. It's just a piece of the overall picture that addresses these particular timing concerns. Those go into standard C or Verilog tool chains to target FPGAs or processors. Or perhaps if you want to render this out as clockwork, you can generate a CAD model and a 3D printer to produce the mechanical model of the timing. So let me try and give you a notional but very specific example of how we use this. On a recent project, we had the need to configure an image compression ASIC. So this is an ASIC that's built onto a digital board with an FPGA and a processor. Its job is to do lossy image compression. But before we can begin to feed the digital pixels to the image compression ASIC, we need to do a fairly extensive configuration process to set up the chip, reset it, give it parameters on how we want the image compressed, sizes, things like that. To do that is a fairly long sequence of configuration bytes passed in over a parallel interface, along with some hardware handshaking. All of those requirements on how to configure this are captured in artifacts like this: timing diagrams, tables of timing characteristics, tables of configuration values. The timing characteristics are pretty important. You have to meet the timing transfer characteristics that are captured here. And so it's a very good candidate for this language. And here we have the solution written in the RITES language. Now, this is illegible. It's not meant to be legible. But what it is the complete source code in the domain-specific language to configure this ASIC. This is everything you need. In fact, this actually has two different configuration paths in this source right here. One is one path where you reset the ASIC and do a from-scratch complete configuration of the chip. Also represented here is a second way of using it, where instead of resetting the chip, you do an update to the configuration on the fly that will take effect with the next image that comes in. It implements everything that you need to do to configure the chip, all those parallel transfers, as well as hardware handshaking. And this is up and running as a Verilog module running on an FPGA at 50 megahertz. So this is a very real-world, complete, realistic example. So everything I've said so far is pretty abstract. I'm going to spend a few slides here kind of talking about what the language looks like, what it can do, what some of the key concepts are. I'm afraid I'm going to have to kind of go fast because we don't have just a lot of time. This is an overview of some of the key things we're going to talk about. Actions. These are how a timing program affects its environment. These are outputs from the module that you would use to coordinate other behaviors. Events are ways that information is brought into the timing module, things that it can detect, wait for, or react to. We have several temporal control mechanisms, such as delay, waiting for something, and then a number of more standard programming concepts like conditional execution via guarded actions and branches. We have a number of loops, some which are more interesting than others. I'll talk about those in a little bit. We'll talk briefly about the data types we have and a little bit about the control interface. So at the top level, this is some of the highest level structures within a RITES program. We have a description string, which is carried over into the generated code as documentation. We have a block that defines data types for these input and output ports. The core sequence block, which explains what happens when. We can support C and Verilog style line comments, arbitrary white space. The language supports a number of different literal types, integers, floating point numbers, for cases where you wish to target C code that don't make a lot of sense in Verilog. We support both C style and Verilog style hex values. You also see some examples of port names and symbols. We have the ability to define constants. Now, data typing. So the RITES language itself is not particularly strongly typed. That's because data type is much more associated with the target language. And data types mean very different things if you're talking about going to generating C code or generating Verilog code. And that's why we broke out this type block within the top level of the program. It's the ability to assign types to the ports that you identified in the main part of the program. We do limited type checking within the RITES language, but it does let you assign data types arbitrarily based on the target language. So you see some examples here where we have an int and a double, which would be useful in C, and then at the bottom, you have that 15:0, which is a 16-bit width that you would use in Verilog. You would never use these all together, but those are examples. We do have default types if you don't want to generate a type. We also have some more exotic ports, which one of them is the internal port, which is basically just a scratchpad memory that you can use within your program without having it enter or leave the module. The reason we separated this typing out is because you could create a timing language program, a sequence of events, of actions, that is independent, totally independent of the type, and use different type blocks for different execution environments with very minimal changes to your main business logic of your timing program. Actions. Actions are ways in which the module affects the world outside itself. We have some very simple ones where you set a port to a particular value, or you copy the value of some other port. We also have the ability to increment and decrement. A little bit more interesting, we have the ability to pulse a port. And so when you encounter this kind of action within the flow of your program, and you tell it to pulse the port, you're saying, put this value on the port now, and on the next time interval, and I'll talk more about time intervals in a second, on the next time interval, let it take some other value. But you don't have to worry about when that other time interval happens. You can follow this statement immediately by a six-way branch. It will just take care of making sure that that update value gets assigned to all those branches. You don't need to keep track of that. You can do it either a default value of 1 and then 0, or you can specify the value. We also have the ability to do what we call tracking actions. This is basically assigning a port should take the value of some other port delayed by a certain value. So basically allows you to phase shift signals coming through your module. Events are the opposite of actions. These are the ways that timing language program can sense its environment and react to things coming in from the outside. So we have standard suite of relational operators, greater than, less than, not equal to, that kind of thing. But because this is a timing language, we also have some temporal operators. So we have the ability to detect falling edges or rising edges or changes on ports. Falling and rising represents a change to or a change from a 0 value. And when you compile a timing language program, it takes care of creating all of the infrastructure you need to detect those changes. So if you're interested in detecting a change, one symbol there is all you need, really, to have it implement all that infrastructure. And then in addition, we have standard logical operations and or not to combine and build up larger events from these basic ones. These are some of the basic sequence flow operations. Stop and restart are keywords that tell you simply to stop the sequence of operations or restart from the very beginning immediately. Then you see several of our delay operators that either wait one time interval, wait several time intervals. You can see we have symbol mechanism of defining constants that you can use here. So this is a way of implementing delays. The wait for statements indicate that the flow of events should wait until this event is true. So in the top there you see the wait for a rising edge on A. Wait until you see the input port A rise from 0, and then proceed in the sequence. This wait for operator can have a timeout. And then finally, in the examples on the bottom, we have timers. These are concurrent free-running timers that are initiated at some point in the sequence flow, will create a signal that you can check later in the sequence flow, but are totally independent of what else is going on. So it allows you to create some concurrency within a particular timing program. We have a number of looping and branching mechanisms. We have several different variations of repeat operator, which take a subsequence of operations and repeat them either forever or for a particular number of times. We also have the ability to repeat over a list, which is the bottom example of the repeat there, where you repeat once for each item in the list, and you can use the contents of those lists differently. We have a while operation, which just checks an event and makes sure it's true and continues looping while it is, with this as a max iterations timeout. with simple if-else-if branching. We also have a pipelined loop. What the basic idea behind this is you wish to iterate, repeat a sequence of operations, but you want to start the next iteration before you finish the first. And this pipeline mechanism lets you do that automatically. So you create a pipeline there, either repeat infinitely, you can do a certain number of iterations, you can repeat based on an event. And the idea is it will begin the sequence of operations you've expressed. At some point in that sequence of operations, you'll hit a fork keyword, which will cause it to begin the next iteration while it continues on from there. And it will do a lot of error checking to make sure that there isn't any sort of conflicts with ports being assigned multiple values. The compiler will take care of making sure there's no conflicts. But it does substantially simplify the implementation of any sort of pipeline computation. So that was a very, very fast introduction to the language. Here's a very, very simple example, but it's a complete program and one you can read this time. What this does is this little program is designed to convert an edge, so some sort of a rising edge in this case, that may or may not be of any known duration, and convert that into a single clock interval pulse. This is a complete code. So we have an input and output. We start with setting that output to 0. And then we repeat forever, waiting for a rising edge on the input. When we see that rising edge, we pulse the output and go back to wait for a new rising edge. If the input is high for a very long time, we'll only get one pulse out because we're waiting for a rising edge. Pulses will be just one clock interval in duration. So some fairly complicated timing behavior captured in very few lines of code, but are very easy to read and understand what's going on. At least I hope. So I've been talking about time, but I haven't really explained what I meant about time. It's time we do that. So time is captured in this language by a very abstract concept called a tick, just some discrete time interval. That tick is provided by the execution environment, and that the nature of the tick will vary depending on what the execution environment is. It is anticipated that the tick would be periodic. That's strictly necessary, but generally it's most useful if it is. So if you implement the timing program in C, it's going to be realized as a function, and the tick will be the interval of a function call. So for every time tick, every interval, you call the function, and it will handle everything of keeping track of time and executing the sequence you've asked for. This can be made very periodic, even on a busy processor, by, say, tying that to a periodic interrupt. If the timing language module is implemented in Verilog, that tick is an FPGA clock edge, which of course is strictly periodic. Often very fast. We have a mechanism to slow down the rate of ticks with an enable input to those modules. Not really necessary. The only reason you want to do that is if you have relatively long delays and you don't want your counters to get too big. It's a means of doing that. So when we take a timing language program and generate C code to implement that functionality, what we get is a function. And like I've been saying, this is not a complete solution to any problem. It's meant to be rolled into a larger code base to implement a system and solve a problem. So the rest of that software is responsible for calling this function periodically. But this function will automatically maintain all of its internal state, keep track of its port values, histories as necessary, its state within its process, counters, loop counters, all of that will be taken care of automatically. Inputs to the module arrive as passed by value parameters to the function we create. Outputs, the module will keep track of all its outputs internally, but it will also write those output values on every call to values that are provided as pointers to the module, to the function. And we have support for all of the timing features. Those are all captured internally with static variables within the function. Now, if you take that timing program and generate it as Verilog, and to be clear, you can take almost any timing language program and go to C or go to Verilog just by different options when you call the compiler. But when you do go to Verilog, you get a Verilog module. Inside that module, you have an optimally sized state machine, optimally sized delay counters, loop counters, using as few resources as we can. Here, the port interface as input and output ports, concepts are a little bit more natural to Verilog than the C call. But it will handle delay lines for all the temporal events, for tracking, It will handle all the logic for generating output pulses, as well as derived inputs and outputs. It also implements concurrent timers with the timer keyword we saw. For Verilog, we also have the option of providing an external counter. Because very, very large counters, you can get two problems with the size of the carry logic. You might want to have a more optimized external counter. That's supported in Verilog. Now, as I mentioned at the beginning, we also support generation in Verilog with triple modular redundancy. A couple of flavors of that, actually. The idea behind triple modular redundancy, or TMR, is to provide protection against single event upsets in FPGAs that are not radiation hardened. The way these manifest often is that the value of a user flip-flop will change, go from 0 to 1 or 1 to 0, without being meant to on the logic you've implemented. And in local TMR, we resolve that by creating 3 different copies of each register and then feeding all 3 of those copies to a majority voter. The idea here is if an SEU comes in and flips one of those bits in one of those registers, the output vote will still have the majority and will still be correct. That result is used and fed back into the combinatorial logic, refreshed into those registers so they're automatically corrected immediately, and you basically experience no impact from the upset. However, this only really protects user flip-flops. It does nothing to protect against configuration memory. So if your logic changes, all bets are off. And in those cases, either you're implementing this on a radiation-tolerant device where the configuration memory is radiation tolerant, it's just the user flip-flops that aren't, or you're relying on scrubbing to go through and fix that configuration continuously. If, however, you want a higher level of protection, we also support distributed TMR, which is implemented in accordance with this diagram. So here, not only do you triplicate all the registers, but you triplicate the voters and all the combinatorial logic. Basically, you create 3 full paths through the design with the voters grabbing copies from each path, creating a majority decision, feeding that back into the logic, updating the registers. So in this case, if you do have a configuration memory upset, maybe one of the voters' operation has changed, maybe the combinatorial logic operation has changed. Nevertheless, 2 of the 3 paths coming through the design will still be correct. So this provides a greater level of protection with greater resource usage. So in the RITES Verilog generator, whether or not you want to use TMR, local or distributed, just a command line option. All of his TMR mechanisms are inserted automatically. So all of his copies of registers, all of the voting and the interconnections, all automatically generated. We do exclude some language features just because it gets too complicated to do all of this with all the language features. For local TMR, we get register triplication, voting, feedback. We implement the state machine with a Hamming code to protect it against errors. For the distributed TMR, we do full 3-path replication with feedback correction for all the registers. So at the beginning, when I explained why we even took on this research, one of the things was the amount of code you had to write to create this timing infrastructure. And this is just a notional, but at least quantitative analysis of what kind of benefits we actually saw. This is looking at that code that I talked about briefly to configure the ASIC. It took us 85 lines of RITES code to do that ASIC configuration sequencing. I went through and manually recoded that using our standard practices. Exact same functionality, but I required 341 lines of hand-coded Verilog to get there, 4 times larger. Now, the generated Verilog was a little bigger than that, about 1.3 times what it took me to code it by hand. So we do see a little bit of increase in code size, and honestly, probably a little bit of increase in resource usage with RITES. But still, the productivity enhancements are significant. This gets really interesting when we start talking about TMR. The generated local TMR required almost 2,400 lines of code, which is 5.4 times larger than the generated code. If we assume that scaling factor is accurate, we'd be talking about hundreds of lines of manually coded TMR. It's even worse for DTMR, where we see 7x increase over the standard generated code. So particularly when we start talking about needing to provide TMR protection, we see some real benefits in code size, at least, from the timing language. So I'm very nearly out of time, but I want to talk about one more more involved example, a way we've used RITES. This is actually a terrestrial example, but it's very close to other TDMA communications protocols we've implemented. This is a sensor data collection system where we have two kinds of devices. One is a master device, and then we have any number of slave devices. The slave devices in this protocol are very low power sensors. They're executing a low duty cycle protocol to preserve their battery life. And so this communication process, the master initiates by sending a long signal that the slave devices detect on their duty cycle wake up, and then they respond with data. This network is completely uncoordinated, so we don't know what devices are out there. There may be thousands of devices possible, and a dozen that we can see at one time. And so they're basically doing a kind of slotted aloha with some randomization and repeats to try and make sure we get the data through. You see the protocol unfold there on the bottom. Various different signals must be sent by different devices over the execution of the protocol with fairly tight timing requirements on when these time slots are, when different events happen, those kinds of things. Here's a little notional example of how we use the timing language to build this system. Again, this is just a piece of it, but the piece kind of coordinates the operation of everything else. There's a timing module, which also works with data command and control elements of the software, with signal processing software, and is also used to control the radio hardware in order to execute this protocol with precise timing, to control the radio hardware, to warm it up in time so that it's warmed up and ready to transmit when the opportunities come up, and to coordinate the signal processing, to schedule the bursts, and also to coordinate synchronization between devices. So again, we compiled this to Verilog, ran it on 128 megahertz FPGA. But importantly, we demonstrated the maintainability, extensibility, and enhanced productivity that we were hoping to get out of this. As this project unfolded, we had to deal with changes to the high-level protocol. We realized there were different signals that had to be sent. Changes to the low-level component control timing, changes to how we could use the radio hardware, what kind of warm-up times it needed, as well as changes to the interface, command and control interface and the rest of the software. So all of these caused fairly significant changes to what the temporal behavior was, and we could very easily, seamlessly, and with very little debugging or reintegration time, make those changes in the RITES program, put them back on the FPGA, and have the protocol running with the new requirements implemented. So just to summarize what we've got, we have a formal, precise, expressive means of describing and reasoning about temporal behavior. These timing language programs are portable between execution environments. We can compile them to C, we can compile them to Verilog, a few other things. We can easily implement these on a lot of different hardware. We definitely see enhanced developer productivity when addressing these kind of timing concerns in developing software. Because it captures the temporal concepts directly in the language, you can reason about them directly. You have to write a lot less code because the compiler builds the timing infrastructure. You don't have to do it by hand. Also, the compiler gets it right. You don't have to worry about debugging it. And we have the proven code generation tools that produce good executable code. We've also seen improved extensibility of the software. We can implement changes to temporal requirements directly, and we can modify timing without having to rework and retest and change the underlying timing infrastructure. And of course, I've talked about a couple of target languages that we've implemented and used a lot, but there's always the possibility of extending this and targeting other languages. Probably our next one will be Simulink, so we can start rolling these kind of timing behaviors into a modeling environment. So that's the end of the talk. Happy to answer any questions.
Yes. Hold on.
Yeah, Martin Panevsky, Aerospace. Question I have is, if you are asking the hardware to do 2 different or 4 different things at the exact time, the same time, but just that's not physically possible, how would this tool know about it, and would it know about it?
So that would depend on, first it would depend on what hardware you're targeting. on an FPGA, it is possible to do 4 things simultaneously. In software, it's going to be simultaneous within the context of whatever the timing tick is for that environment. So for a C implementation, if you have to do 4 things simultaneously, you'd make one call to the timing module, and it would return those 4 things all as responses to that same call. So they would not be strictly real time then in an actual nanosecond by nanosecond sense, but they would be real time and simultaneous within the context of the call sequence to the program.
Okay.
Christian Vidi from TD Tech. Have you also compared the number of gates, for example?
No, I haven't had a chance to do that. I don't think we're bad, because we tried very hard to keep everything sized as well as we can. I'm sure there's a little bit of creep relative to what you could do with really optimized hand carriage.
Okay, we've got time for one more question.
Mike, is there a limit, the relationship between the tick size and the number of things that you can get done in that tick? Does the language take care of that?
Yeah, there's no language limit on that. Eventually, you'll run out of resources, but it would be a pretty big design.